Good morning, conference judges. This is Asadi Srinivasulu, working as a research scholar under Professor Anupam Agrawal, and my co-authors are Ekeshwar Aditya, Shreya Bharati. Today's my conference paper title is Enhanced COVID-19 Diagnosis by integrating various machine and and uh, deep learning techniques for improved chest X-ray classification. So these are my contents: abstract, introduction, literature review, research gaps, proposed methodology, data sets and experimental setup, results and discussion, comparative analysis, conclusion and future work references. So COVID-19 diagnosis from chest X-rays is needed, but limited positive samples cause overfitting and weaken convolutional neural networks performance compared to slow resource heavy on RT-PCR test. So that's why we are taking chest X-ray images for our research. We are using generative adversarial network based data augmentation with a quality filtering mechanism guided by visual checks and metrics like SSIM, PSNR to keep only high quality synthetic images for training. And finally, we have filtered GAN augmentation improves model reliability and accuracy versus using unfiltered synthetic data, addressing data scarcity for medical image classification. Coming to introduction, the COVID-19 pandemic severely strained healthcare systems, creating a critical need for rapid, scalable, and reliable diagnostic methods. And deep learning, especially convolutional neural networks, has shown promise in analyzing chest X-ray images. For COVID-19 detection, we have collected nearly 5,000 chest X-ray images from free available repositories like Kaggle and GitHub. The research proposes a progressive growing generative adversarial network, that is PZGAN, based on synthetic data generation approach combined with filtering to strengthen model performance and address dataset limitation. And we have collected nearly 5,000 samples from various repositories, and I have collected 15 literature survey papers from reputed journals Springer Nature, ACM, Elsevier, Inder Science, Hindavi, and scientific reports, etc. And these are the major columns I have segregated: author names, limitations or issues or challenges, existing method, proposed approach, data set utilized, techniques applied, what are the tools they have utilized, validation metrics, future directions, and references. So research gaps, we have identified 5 for this research paper. Data scarcity, data sets are very small and imbalance, limiting deep learning generalization. Synthetic data quality, so many GAN generated images lack diagnostic realism, introducing noise into model training. Overfitting risk is one more research gap we have identified. Reliance on limited data sets causes models to overfit, reducing robustness in real world deployment. Lack of cross dataset validation. Most studies validate only on a single dataset, missing broader generalizability. Explainability deficit. Current models often lack interpretability, reducing their trustworthiness for clinical adoption. And this is the proposed methodology we have applied. And this PGGAN based augmentation and filtering process, detailing how synthetic chest X-ray images are created and assessed for quality and carefully selected before being added to the training data set. For training data set, we have classified into 80% of images for training and 20% for testing to improve the model's accuracy and reliability. And the results, we have successfully applied PG, GAN and deep learning methods, CNN, and we have achieved significant improvements in classification accuracy and robustness compared to baseline CNN and unfiltered GAN methods. Experimental evaluation showed a higher F1 score, precision, and AUC, confirming that filtering synthetic images before training prevents noise and enhances generalization. So finally, we are comparative analysis demonstrated that the method consistently outperformed traditional augmentation and existing GAN models, highlighting its clinical applicability for reliable COVID-19 X-ray detection. So this is the comparison of validation accuracy across baseline, generative adversarial networks, augmented models we have incorporated and leveraging with ResNet 50 and Inception V3. So we have applied baseline CNN, that is original, and original only ResNet and Inception 3, balanced trade ResNet 50 is Inception V3, unfiltered PGGAN ResNet 50 we have integrated, and filtered PGGAN ResNet 50 and Inception V3. And finally we are showing in x-axis validation accuracy, x-axis. In y-axis we are showing validation accuracy. We got very good accuracy for Inception V3. And this is the comparative analysis with three models with integration. Baseline CNN model, we got accuracy 85%, and CNN without augmentation showed lower robustness. Unfiltered GAN plus CNN, we got 88%. GAN augmentation without filtering slightly improved results but added noise. And the final model proposed filtered PGGAN plus CNN, we got 94 accuracy. Our method outperformed baselines with significantly higher accuracy and robustness. The conclusion and future work: enhancing training with the filtered PGGAN generated chest X-ray images alongside original data, improved classification accuracy and robustness. Filtering GAN outputs was essential to prevent artifacts and misbalanced structures, mislabeled structures that could reduce model reliability. The future work explore larger and more diverse multimodal datasets like X-ray and CT to strengthen generalization across populations, integrate explainable AI and federated learning to ensure clinical interpretability and privacy preserving development. These are the references we have collected. 16 literature survey papers we have connected. And so this is about enhanced COVID-19 diagnosis, leveraging GAN based image augmentation and deep learning for improved chest X-ray classification. Thank you for giving me this wonderful opportunity. Is there any doubts? Please you can raise any question related to this paper. Thank you so much for giving me this wonderful opportunity.